Okay, so the first thing is taking a look at a regular polygon. Okay, regular polygons, again, have all equal sides, all equal angles. Okay, and if you were to locate the center of a regular polygon, what you would see is it also happens to be the center of a circle that can pass through all the vertices of that regular polygon. The reason this can be useful is if you connect all the radii, so the vertex of the polygon to the center of this circle, what kind of shapes are created here? Okay, and specifically equilateral triangles, right? All of these are radii of the same circle. Okay, and so when you look at the area of these regular polygons, really what you're doing is you're finding the area of one triangle, which is found by the area 1/2 base times height. And then how many triangles do you have in this case? 6. It's going to be the number of sides of whatever your polygon is, your regular polygon. And so you can derive the formula, the area formula for a regular polygon very quickly if you don't want to memorize it. Okay? And when you look at this, the base of, so let's take one of these reference triangles. And I'll refer to these isosceles triangles as reference triangles. Here's the base of this reference triangle. So when we look at the area formula, we have 1/2. Well, the base is going to be representing this length of the side of this figure. So S represents the side length for your regular polygon. The H, the altitude or the height of this reference triangle, is referred to as A, the apothem. Okay, so A stands for, or the term given to this is the apothem. The apothem is the perpendicular distance from the center of a regular polygon to its side. So the segment perpendicular to the side that passes through the center is going to be called an apothem. Easiest way to think of it, A simply stands for altitude. It's just the altitude of that reference triangle. Okay, and then N stays as it is, the number of sides. So here is your area formula for any regular polygon. The area is equal to 1/2 SAN. Okay, again, it's only true for regular polygons, but that is your formula. Okay, now let's take a look at a problem that has to do with a regular polygon, and one that you're very likely going to see. And that is, let's take this regular hexagon again. If I ask you to find the area of a regular hexagon whose side equals 10 units. Okay, so you know that this length is 10. Your area formula is 1/2 SAN. You can find all but one piece of information already, right? You can plug those in. You have 1/2. What's the length of the side? 10. The apothem you don't know. And what's the number of sides? 6. Okay, so anytime you're working with area here, it's probably useful to draw in or sketch just one of those reference triangles. That's all you need to sketch. In working with this triangle, you have enough information to find all the pieces that allow you to identify this apothem. Okay, what type of a triangle is formed in black here? The reference triangle of a regular hexagon is, it's equilateral, right? That's unique only to a regular hexagon. Okay, a regular hexagon forms 6 equilateral triangles. So when you draw in the apothem, what type of a triangle do you create in here? It's a 30, 60, 90 right triangle. Okay, so when you cut this, when you draw your altitude of any isosceles triangle, what's it going to do to the base? Bisect it, so this side is 5. And if the side opposite 30 degrees is 5, what does that mean the side opposite 60 degrees has to be? Based on the special properties of a 30, 60, 90? 5 root 3. So there's our apothem, and now you can multiply those through to get your total area. Okay. Let's take a look at some of these relationships, because it's not always going to be a 30, 60, 90. This is the only case where this works. And I want to take a look at a couple properties here. If you draw in, if you wanted to find what each angle is in this regular polygon, how could you solve it? There's a couple different ways as a review from yesterday. What's one way to find each interior angle of a regular polygon? Okay, so one is to use the formula, n minus 2 times 180, the sum of the angles, all divided by n. Okay, or what else could you do?
Supplement.
Okay, good. You could take the supplement of its exterior angle, 360 over n. So either of these formulas or equations or relationships can allow you to find what this each interior angle is. How does each interior angle relate to the base angles of these reference isosceles triangles? The reference triangle is going to have an angle that is exactly what compared to each interior angle of the whole regular polygon? Half of it, right? Because these are going to be equal. Therefore, when you look at this other triangle, these will also be equal to these. So they're all going to be the same. It's half of each interior angle measure. So when you're looking at these little isosceles triangles as references, you need to be able to identify that this angle right here is 1/2 the total interior angle of the regular polygon. Okay, there's another relationship that you can identify here, and that is, if you look at this, you have, I'm going to call this angle x, half of the interior angle. This other angle here that forms the whole thing is also x. And then this one right here is 180 minus x, correct? Because it's the, 180 minus 2x. It's the linear pair, the exterior angle. And now, if you look at this whole isosceles triangle, you have a base angle of x, a base angle of x. What's this other angle, this vertex angle, going to be? Well, in this case, exactly 60, but let's say in terms of x, what's the total sum of those three angles? 180. So this angle is going to be 180 minus 2x. So what do you notice about the vertex angle of your reference triangle compared to the exterior angle of your regular polygon? They're exactly the same. Okay, so you can use this to help guide your work as well, and I'll show you how in just a second.